So let's get back to our general discussion on distributions or image measures, okay? So let's say we have nu equals mu of x pre-image. So what does that mean? We calculate nu of d as the probability or the measure that x is in d. Okay. So on one hand, I can see this as an integral of nu over the set D. Okay. And since this is x inverse x pre-image D, okay, we can see it as the indicator, the integral of the indicator of x inverse D, or let me write it this way, the integral with respect to mu of this set over this set, right? Which I can also write as the indicator of x pre-image D, d mu, or the indicator of t applied to x, d mu. So that's an integral over omega. That's an integral over omega, whereas this is an integral over d. Or let's write it in the whole space, like indicator d times d nu. So just to write it in short, what we have is that we have the integral of this indicator function applied to x. Now that's a random variable on omega, d mu, okay? This is equal to the integral of the indicator function itself without any reference to x. And now it is d nu, which is mu of x inverse, x pre-image. And that is over the whole set E. This we have for every d. Okay. So this is like, I'd like to calculate the probability that x takes values in d. So I need to, in theory, I need to calculate an integral over omega. On the other hand, I can equally calculate it as the integral of this indicator function, which is a function on E. It's a function on E. And I need to integrate it with respect to the image measure, which is on E. Okay? So that's an integral on omega. That's an integral on E. So this is like a change of variables formula. You have an integral on this space. It suddenly becomes an integral on the value space, image space. So the nice thing about this is that you can rewrite it in a much more general way. You can replace these indicators by any positive measurable function. For every f from E to R bar plus measurable, we have the integral of f applied to x d mu is equal to the integral of f, just the f, just this numerical function f, with respect to the measure nu. Let's first prove it. So if f is an indicator, this is already checked, right? Done already. If you have So let's say AI indicator DIs, 1 to n, simple positive function, okay? Simple positive. Then let's check the result. Well, the integral of f of x d mu over omega is this function applied to x. But since I have different sets, I can apply this indicator function to x for each I and add those results. It's going to give the same effect because I'm doing it value by value, right? So this is d mu. So now it's a sum of those functions. By linearity of integral, I can swap the order of the integration and summation. And by the previous step, I can write this as an integral over E, indicator di, d nu. So now we are using the previous step, the thing that we just checked. And if we use the linearity again to reswap, so now it's the sum of those functions d nu, which is f. So this is f d nu. And finally, what you need to do is to let fn converge to f, where fn is simple positive for each n, right? So in that case, you have f of x d mu, which is the limit of fn applied to x d mu. And now what type of result should we use to swap the order of the limit and the integration? Fn's increase to f, fn of x's increase to f of x. What is the convergence result that we should refer to? Integral of limit equals limit of integrals. How can I say that? Yes. Say it again. Monotone convergence theorem, because fn's are monotone, increasing f to f. Therefore, if you apply fn to x and let n go to infinity, fn of x will also form a monotone increasing sequence. So by mon, this is limit of integrals. Okay, I'm out of space, so let me continue here. Now what? Now this is the integral of fn of x, where fn is a simple function. So we can use the previous step to replace it by integral of fn with respect to d nu on E. So what is done follows, what follows then is that we have limit of fn's d nu, which is just f. And what do I use here? That's not a tricky question. So what is the answer? What theorem? Again, mon. Yeah. So you use mon twice, just as you used linearity twice in the previous step. As I said last week, this approach, starting with indicators, pass to simple positive functions, and then pass to their limits, which are general positive measurable functions, is a lifestyle, right? So we really follow these steps. Every time we need to prove something that is valid for every positive measurable function. You already have it for indicators. So whenever I give this to you as an exercise, as a homework problem, you should always think, hey, I can check this easily for indicators. So let me start with indicators. And then maybe I can pass to simple positive functions, and then later general positive measurable functions. Okay? The nice thing here is that the case where f is an indicator function is just the definition of nu. It's just by the definition of nu. So then you use linearity to pass to simple positive functions, and then monotone convergence theorem to pass to arbitrary positive measurable functions. So we showed it in 3 steps. So we're done. Why don't we stop? Why do we stop at this point? And why don't we talk about general functions with positive and negative values? Well, you can do it, but then you have to impose integrability conditions. So usually it is the natural way, the natural point to stop is positive measurable functions. You can do all your theory with positive measurable functions. But if you like, you can always extend it to arbitrary measurable functions. But then you have to worry about the integrability if you have infinity minus infinity case. This you don't have in positive functions. That's why we state this theorem for positive measurable functions. Anyway, there is a nice corollary to this. Okay? Let nu be a measure on E. So now I'm not saying this is the distribution of X, okay? Let nu be a measure on E. Then we have X has distribution nu if and only if the integral of f of x d mu is equal to f d nu for every positive measurable f on E. So this is on omega, this is on E. For every f. So why is this true? Well, first of all, if x has distribution nu, that is, nu is just mu of x inverse, we have the result by the previous theorem. This is what the previous theorem says. So one way is just from this previous theorem. So here we have, this is mu of x inverse, right? I said this at the beginning. Here I start with an arbitrary measure. So if mu is the distribution of x, if we're in that framework, then we have this result. Okay? So that is just a restatement of the theorem. The converse is nice. So if you have this for an arbitrary measure nu, then you can make sure nu is in fact the distribution of x. So how can we say it? How can we say it? Well, we can specialize into indicator functions. So suppose, let's put a star here, okay? Star holds for every f measurable. In particular, take f equals indicator d for some d, which is a measurable set in E. We get what? This integral gives us mu of x is in d, and this integral gives us nu of d. So nu is mu of x inverse. Just the calculation that we did here, right? This integral, indicator d applied to x d mu, is the measure that x takes values in d, whereas this integral, indicator d, d nu, gives the probability or the measure that, that is assigned to set d. So if you have it for every d, then this means nu is the distribution of mu, or the image measure of mu under x. So the probabilistic version is also very nice. I mean, there is nothing to prove for the probabilistic version. I will just replace everything with expectations and so on. So x, so we have mu equals p is a probability, and we have x is distributed by this measure nu if and only if we have expected value of f of x is equal to f d nu on E for every f from E to R bar that is measurable. If E is, let's say, the real line with the Borel sigma algebra, then the integral becomes an integral over the real line. So the question would be that can we calculate such an integral on the real line using Riemann integrals? Although nu is not the Lebesgue measure. So if there is a way to convert this integral on the real line to an integral, to a Riemann integral, that would be very cool, because then we can use our calculus results to evaluate the integral. So far we have discussed distributions, and at least distributions are useful in rewriting certain expectations. So I need to calculate an expectation which is defined as an integral over omega, which is abstract. But maybe I have a real valued random variable, so that's an integral on R. But not with respect to dx, the Lebesgue measure, with respect to some distribution. So in other words, starting with some random variable, I can find out the distribution of it. But what is the relationship between the distribution of x and some a priori distribution, a priori measure given on E, like the Lebesgue measure, like the counting measure on a discrete set? What is the relationship between our distribution of a random variable and some canonical standard measure on the given space, on the real line, on a countable set? So to that end, we're going to discuss this relationship, namely the relationship between some measure and another measure. So we're going to discuss one measure which is given on our space. We're going to call it lambda. So let E lambda be a measure space. Okay? So let nu be some measure. In particular, it can be the distribution of a random variable, some measure on E. So the question is, what is the relationship between nu and lambda? Let me write as an example, just in your mind, always consider lambda as the Lebesgue measure. Okay? So it's a standard measure. Okay? So here's a lemma. Okay? So let lambda be given, and let h be a function from e to r bar plus that is positive and measurable. Be a measurable function. Define nu as the integral of h d lambda over the set D. So it is the integral of h indicator D d lambda. If you like, you can put x. Then nu is a measure on E. If nu is a probability measure, if and only if hx lambda dx over the whole space is equal to 1. So let's check it. So I start with the Lebesgue measure, let's say, and I pick a function that is positive. Okay? I use h like a density, okay? Like a density, meaning that I create a new measure out of lambda, out of the Lebesgue measure, by integrating hx dx over the set D. Hx dx. If this is the Lebesgue measure, this is hx dx, right? Over the set D. And this defines a new measure for me. Okay? So this is only one way. If you're given lambda, you can create new measures out of lambda. Okay? We haven't looked at the converse. We are still not looking at this question. Okay? We're creating new ourselves. We're not taking new as given. But anyway, at least there is a way to deviate from a given measure. At least if you're given the Lebesgue measure, there is a way to find another measure. Okay? And this is by fixing some density. Okay, let's check it. So nu of empty set is, well, just 0 because it's hd lambda over the empty set. And empty set is null, therefore it is 0. And if you have d1, d2 in E that are disjoint, so this is 1, this is 2, then nu of the union is what? It's hd lambda over the union. And last time we had a theorem which says this is the sum of the individual integrals because these are disjoint sets. So you can integrate them one by one. First on D1, then on D2, then on D3, and add all the integrals. And this is nu di. Therefore, we have countable additivity. So nu is a measure. And nu is a probability if and only if nu of omega, nu of E is 1. But what is nu of E? Nu of E is just h d lambda over the whole space, just this condition. Okay, so here we have nu d, which is the integral of nu on the set D, right? And this is defined as h, let me write it this way, indicator D on E, okay? And this is h indicator D, d lambda. So we're working on just one space, okay? This is not the previous result. We're just working on one space. We are given one measure, and we create another using this H. Okay? So if you'd like to see it this way, nu dx equals hx lambda dx. In short, we write nu dx equals hx lambda dx. So, or h is, or let me write it this way, h is d lambda, sorry, d nu over d lambda at x, at x. And we say H is the density of nu with respect to lambda. Okay? That's a very nice way of writing it. Okay? So this looks like a differential form, right? But this is really how you define your new measure nu. Okay? You multiply your old measure by the density, meaning that to calculate nu of d, what you need to do is to integrate h times lambda over d, h d lambda over d. So if you just forget about the integral signs, you can write it in short like this. Or like this, which doesn't mean like division. Okay? So this is like the differential calculus, right? The derivatives. They're not ratios or it's not a over b. You know it, but it's the derivative, right? So that's the nice thing about it. And in fact, you don't need to specialize into indicators. So just one lemma. In the above setting, we even have fd nu equals fhd lambda for every measurable f from e to r bar plus. And the proof is exercise, meaning that just do for simple functions, indicators, simple positive functions, and then to positive measurable functions. The same type of proof that we have just done in this change of variables formula. Just follow the same approach, the lifestyle. So one message is that there is no big difference between indicator functions and general positive measurable functions. Okay? Integrals are linear, and they have the monotone convergence property. So whenever you have a result for indicators, in most cases, you can extend it to positive measurable functions, okay? Following this program. So the question is still this. What if, so if lambda and h are given, then we can create a new measure, nu. If lambda and nu are given, does there exist a density h such that d nu is hd lambda? Does every measure have a density with respect to the Lebesgue measure, with respect to lambda, a given measure? So the answer is yes, in good cases. So let's define what a good case is. Let nu lambda be measures on E. We say nu is absolutely continuous with respect to lambda, and write nu absolutely continuous with respect to lambda if for every set D we have lambda 0, lambda of D equals 0 implies nu of D equals 0. It's a very important property. And whenever we have nu absolutely continuous with respect to lambda, we're going to have a density. We're going to have a density. So what is the meaning of this absolute continuity? So let's say you have a region in E whose measure is 0. Okay? Let me draw another picture, not like this. Okay? Let's say this is like the real line, okay? And let's say this is like R2, okay? And let's draw a region whose area is 0. So this set has area 0, right? So let's say you have a measure, okay, which measures area. Like the Lebesgue measure on the real line, there is a measure on R2 which measures area. Okay? Then if you have a set of area 0, you call it a measure 0, a set of measure 0. So that's a null set for that measure. So if you have this property, okay, and nu, so here lambda of D is 0, if you have another measure which is absolutely continuous with respect to lambda, then we must have nu of D equals 0. So nu is not free too much. Nu has to assign 0 measure to that set if lambda already assigned a 0 measure to that set. Okay, let me give you one example. Let's say we're on the real line with the Lebesgue measure. And let's say we have a fixed point. Okay, nu is the Dirac measure at point 0. We didn't use brackets like this, right? We just put 0. Dirac measure at 0. Okay? So we don't have nu absolutely continuous with respect to lambda. Let's draw the real line. Okay? So the Dirac measure at 0 just puts 1 kilogram on point 0, okay? And no other mass on everywhere else, whereas the Lebesgue measure measures the length. Measures the length, okay? So if you look at the Lebesgue measure assigned to the singleton, what is it? What is the Lebesgue measure of set 0? Point 0. 0, because it's a singleton, right? It's a countable set, so it's 0. Whereas the Dirac measure of this set is what? 1. So that's a counterexample to being absolutely continuous. And we even don't have the other way around. Okay. Anybody who wants to give an example of a set whose Lebesgue measure is non-zero, but Dirac measure is 0? A set, yes? A set that does not include point 0, okay? But you must also have Lebesgue measure strictly positive, so let's take an interval maybe, okay? Let's pick 1 to 2. So the Lebesgue measure of the set 1 to 2 is non-zero, it is 1. But the Dirac measure of the set 1 to 2 is 0, because it doesn't include point 0. So this is not absolutely continuous with respect to this, and also this is not absolutely continuous with respect to the other. So this is not always the case. That's the message, okay? But if this is the case, we have a very nice theorem called Radon-Nikodym theorem, which we're not going to prove. It would take at least 2-3 hours to prove it, because one needs to go through either to Hilbert spaces or to sign measures, both of which requires a lot of heavy machinery. So I'm not going to go into that. So that's a result, like the existence of Lebesgue measure. That's a result that we're just going to take for granted. Okay? We're not going to prove it. Let nu lambda be measures on E. Assume they are sigma finite, and nu is absolutely continuous with respect to lambda. So sigma finiteness is also necessary. And remember, Lebesgue measure is sigma finite. Sigma finite means what? You can create sets which partition the whole set, and each set has finite measure. So Lebesgue measure is sigma finite because you can create intervals 1 to 2, 2 to 3, 3 to 4. They all have finite measure. Okay? And if you have a finite measure, it is automatically sigma finite. Okay? Anyway, assume they are sigma finite, and nu is absolutely continuous with respect to lambda. Then there exists a measurable function h, which is going to be the density, such that, let me write a few equivalent ways of writing it. So such that nu is h d lambda. So d nu is h d lambda. Okay? That is, nu of d is h of x lambda dx over d for all d. Same thing. F of x nu dx is equal to f of x h of x lambda dx for all positive measurable on E. So they all mean the same thing, and we proved it, or I left it as an exercise. Anyway. So the thing is that we had a lemma. Where is the lemma? Okay, there is the lemma. So given lambda, given a density, you can create a new measure. Now you start with two measures. They are sigma finite, and this one is absolutely continuous with respect to lambda. There must exist some density. There must exist some density. And again, we use this kind of notation, like the derivative notation. And indeed, we're going to call it the Radon-Nikodym derivative of nu with respect to lambda. So let me add one more statement, okay? In addition, such h is unique up to lambda almost everywhere equality, meaning that if h tilde is another function such that d nu equals h d lambda, then h and h tilde must agree almost everywhere. That is, the set of points at which h and h tilde are different is a null set. So such lambda almost everywhere unique function is called the Radon-Nikodym derivative of nu with respect to lambda, or a version of the Radon-Nikodym. So we write h is d nu d lambda for each such version. In fact, just as a checkpoint, this definition or this representation of nu in terms of its derivative with respect to lambda does not violate absolute continuity. For instance, what does absolute continuity mean? Well, if lambda of a set is 0, then nu of the set must be 0. If lambda of the set is 0, look at here, lambda of set D is 0. This means what? You're integrating over a null set. So this will give you 0. So in fact, this is if and only if. If you have sigma finite measures, nu absolutely continues with respect to lambda, if and only if there is a density, which is the density of nu with respect to lambda, or the derivative, Radon-Nikodym derivative of nu with respect to lambda. Okay? d nu h d lambda. So what does that mean? Whenever you need to integrate, always replace d nu with h d lambda. So the natural next question is, let's say lambda is a standard measure and nu is the distribution of a random variable. So what happens when nu is absolutely continuous with respect to lambda? This is the next question. So in other words, we discussed distributions, we stopped at some point, and then discussed the relationship between two measures on a space, on the same space. So if now my nu is the distribution of a random variable, and lambda is like a Lebesgue measure or a counting measure, is there any interesting relationship between the two? So if there is a density of my distribution with respect to the Lebesgue measure, is this an interesting case? That's going to be an interesting case. So the next time, we're going to discuss discrete and continuous random variables. Okay? One case will be the case where your distribution is absolutely continuous with respect to the counting measure, okay? Counting measure, which just counts points, sum of Dirac measures, okay? The other case is the case where your distribution is absolutely continuous with respect to the Lebesgue measure. So, but of course, the two, they do not form the general case. A random variable doesn't have to be discrete or continuous. Okay? These are just two special cases. Okay? So this is what we're going to discuss next time. We built the theory today, so next time we're going to calculate a lot of stuff about Poisson, Gaussian, gamma, exponential, etc., etc. Okay? So thank you.